It is the diastase of secretion, which will be subsequently referred to simply as diastase, formed during the malting process, which is responsible for the conversion of the starch during mashing, and that this diastase is only capable of acting under the ordinary conditions of grinding and temperature on such of the starch as is contained in cells which have undergone the above mentioned process of modification. From this it follows that if any portion of the barley corn has escaped that change, that is to say, is hard and vitreous like barley instead of being soft and friable like malt, it will in most cases escape conversion in the mash tun and will so be lost to the brewer. It is usually stated as a general proposition that gelatinization of starch by heat must precede its conversion into soluble products by diastase, and whilst this is true of potato starch, it does not appear to be the case with the starch of barley and certain other cereals. At any rate, in a well-made barley malt we have all the potentialities of the change which it is the object of the brewer to bring about. There is starch in a condition to be readily acted on by diastase, and there is more than sufficient diastase to convert that starch into soluble and partly fermentable substances. It will now be necessary to consider briefly the nature of that very important change. It may be said at once that the chemical reactions involved in the diastic transformation of starch are of a highly complex character and are still the subject of investigation. It would obviously serve no useful purpose, even if it were possible within the limits assigned to this manual, to attempt to deal with the various views which have been held by the many chemists who have devoted themselves to this subject, and I therefore propose to state in the simplest language possible the view which is most widely held at the present time, and which certainly offers the most satisfactory explanation of the observed facts. In regard to the composition of granular starch, that is, starch as it exists in various plants, we know nothing save that its empirical or simplest formula is C6H10O5. By submitting this to the action of cold dilute mineral acid, or in other ways, it may be converted into a simpler product which gives many of the ordinary reactions of granular starch, from which however it differs in being soluble in hot water and in not forming a paste or jelly when its hot aqueous solutions are cooled down. This substance is known as soluble starch, and is the starting point of the change which we are considering. It has the same empirical formula as ordinary granular starch, and there is some ground for assigning it to the molecular formula C12H20O10 100. When soluble starch is acted on for a long time by diastase at low temperatures, it is entirely converted into maltose, water entering into the reaction according to the following equation: C12H20O10 plus H2O equals C12H22O11. When, however, the action takes place at higher temperatures, such as those adopted in the mash tun, the starch molecule breaks down in such a manner as to yield maltose, dextrin, and certain intermediate bodies known as maltodextrins or amyloins. The soluble starch molecule may be represented as being composed of 5 units of repeating amylin segments of carbon 12, hydrogen 20, oxygen 10. C12H20O10 20. At the moment of the attack by diastase, this molecule breaks down into its 5 component groups, one of which differs from the remaining 4 in its resistance to the further action of the diastase, and constitutes the substance referred to in the literature of starch conversion as stable dextrin. The remaining 4 complexes, each having the formula C12H20O10 20, then undergo progressive hydrolysis, each C12H20O10 or amylin group becoming converted by the assumption of water into a C12H22O11 or maltose group. Footnote: By hydrolysis is meant the conversion of one substance into one or more other substances of similar molecular formula, usually at the instance of dilute acids or enzymes, such conversion being preceded by the assumption of one or more molecules of water. As each amylin group takes up the elements of water, the resulting maltose group remains a constituent of the complex unit until the last has been hydrolyzed, when free maltose results. Thus the change in the case of each of the 4 complexes might be illustrated by the following scheme. parenthesis C12H20O10 close parenthesis 20 is hydrolyzed into a maltodextrin composed of two subunits, one of 19 repeating amylin C12H20O10 segments, and the second of maltose C12H22O11. This in turn is hydrolyzed into a maltodextrin composed of two subunits, one of 18 repeating amylin segments, and the other of 2 repeating maltose segments. The process continues another 18 times until all the amylin segments are hydrolyzed and 20 molecules of free maltose C12H22O11 result. From this it follows that if the diasters were allowed to act at favorable temperatures for a sufficiently long time, the final products of the reaction would be maltose and the stable dextrin, which is only acted upon with extreme difficulty. If, however, the temperature and time conditions are so arranged as to restrict the action, and this is the case in the brewer's mash tun, then in addition to free maltose and the stable dextrin, a certain proportion of the intermediate products of the reaction, the maltodextrins, will occur. It now remains to consider the parts which these various substances play in the production of beer. Beer differs from many alcoholic beverages in that its flavor and character are quite as much, if not more, dependent on the nature of the unfermented extractive matters than on the presence of alcohol and other volatile products of fermentation. In addition to this, it is essential that it should be capable of undergoing a certain amount of fermentation while in the cask, and often in the bottle, awaiting consumption. The cask fermentation keeps the beer charged with carbon dioxide gas, and without it the liquid would speedily become flat and undrinkable. It is clear from these considerations that the extractive matters derived from the malt or other materials must not be completely fermentable, for if that were the case the resulting liquid would be little more than a dilute solution of alcohol, and would not possess any of the characteristics of beer. It may be mentioned in passing that this is the aim of the distiller, who desires only to produce alcohol, and whose methods are in consequence directed chiefly to that end. It will be remembered that the brewer makes use of malt which has been heated on the kiln to such a temperature as to bring about the destruction of much of the diasters formed during the germination of the grain, and in the mash tun he again employs temperatures sufficiently high to restrict the activity of that which remains. In this way he ensures that the wort, that is, the clear saccharine liquid containing the products of the conversion of the starch, shall contain 1. Maltose, 2. Maltodextrins, and 3. Stable dextrin. Now these substances together fulfill the conditions necessary for the production of beer, the maltose being readily fermentable and therefore yielding alcohol and carbon dioxide gas, the maltodextrins being less readily fermentable, and the stable dextrin practically unfermentable. The readiness with which the maltodextrins are capable of undergoing fermentation depends to a great extent on their composition. Those which contain the largest number of the maltose groups, in the complex molecule being hydrolyzed to free maltose, and fermented much more easily than those containing a larger proportion of the amylin groups. All, however, are capable of being converted into maltose by diasters. The brewer's wort in the fermenting tun does not, however, contain any active diasters, and for the present it will suffice to say that the great bulk of the maltodextrins present in the wort are not fermented during the main fermentation by the ordinary yeast. Since maltose is completely fermentable, and the stable dextrin for all practical purposes unfermentable, it follows that the quantity and nature of the unfermented but fermentable matter remaining in the beer at the end of the fermentation will depend almost entirely on the proportion of maltodextrins in the wort as it leaves the mash tun and on their character. This in turn is dependent on the nature of the malt employed and on the conditions to which it is subjected in the mash tun. Broadly, it may be said that the malt kilned at a high temperature and mashed at a comparatively low one will yield worts containing relatively high proportions of free maltose and of low type maltodextrins, whilst malt kilned at lower temperatures and mashed at rather higher ones will give worts containing less maltose and a larger proportion of high type maltodextrins. The maltodextrins, although behaving in some respects as actual compounds of maltose and dextrin groups, yet manifest many of their properties of mixtures. This is true of their flavor, that of the high type compounds approximating that of dextrin itself, whilst the low type maltodextrins more nearly resemble maltose. In their degree of fermentability the same is true, for the low type compounds are obviously more easily converted into maltose and therefore more readily fermented than those of higher type. In practice this is of considerable importance, particularly in connection with the brewing of beers of various classes. If we take a stock pale ale as representing the one extreme, and a mild ale intended for rapid consumption as representing the other, we shall see that the requirements are very different indeed. The former beer must be of delicate palate, free from excessive sweetness, and must contain a sufficient amount of residual carbohydrate matter to provide for a regular and constant supply of carbon dioxide gas (cask fermentation or conditioning) over a considerable period of time. The mild ale, on the other hand, must be sweet rather than dry, and must be in a condition for drinking within often a few days of its manufacture. For the brewing of the pale ale, then, we require a wort containing a relatively large proportion of maltodextrins of high type, since these are devoid of sweetness, and owing to the slowness with which under ordinary storage conditions they are converted into fermentable maltose, they supply the long maintained and persistent cask fermentation which is a necessary feature of these beers. For the brewing of the mild ale, on the other hand, the wort must be rich in free maltose and in maltodextrins of low type. Such wort will be readily fermentable, and the beer at racking will contain carbohydrate matters sweet to the palate and capable of undergoing the quick cask conditioning which is essential in the case of beer intended to be consumed within a few days of racking. In practice it is found that these two sets of conditions are obtained by employing on the one hand a pale malt, i.e. a malt kilned at comparatively low temperatures, and adopting somewhat high mashing temperatures, and on the other hand by using a higher dried malt and mashing it at lower temperatures. It must not be thought that the range of mashing temperatures within which the brewer has to work is a wide one. So powerfully is the diastase affected by slight variations of temperature within the limits of practical working that 2 or 3 degrees are often sufficient to affect to a marked extent the palate fullness, rate of conditioning, and other properties of the resulting beer. When working on the infusion system of mashing as adopted in this country, and excepting a few little used processes, it may be taken that 145 degrees Fahrenheit and 155 degrees Fahrenheit represent the two extremes, the lower temperatures being employed in the brewing of mild ales, and the higher for the pale ales, stock bitters, and similar beers. It will be seen then that the great importance of the mashing process lies in the fact that it is in the mash tun that the character of the resulting beer is largely determined, the brewer so arranging his conditions in relation to the malt as to produce the type of wort and consequently the class of beer he desires. Various methods have been devised for arriving at a knowledge of the amount of active diastase existing in malt, or rather for assigning to malts numbers, expressing in terms of an arbitrarily chosen scale their relative diastasic activities. Whilst these methods do not bear any simple relation to the conditions of brewery practice, the results they yield are often of the greatest value as showing whether any given sample of malt has been kilned in such a manner, that is to say whether its diastase has been suitably restricted, as to render it well adapted for the brewing of the particular class of beer for which it is to be used. The changes which have been described above and which occur when malt is mashed apply equally to any raw or unmalted grain which may be mixed in the mash tun with the malt. As has already been pointed out, the latter contains more diastase than is necessary for the conversion of its own starch, and so a proportion of starch derived from some other source may be used if desired, the conversion taking place as in the case of the barley malt starch itself. When, as is usually the case, some form of prepared grain such as flaked or gelatinized maize or rice is used, all that is necessary is to mix the grain uniformly with the malt in the mash tun itself, and proceed exactly as if an all malt mash were being made. In the manufacture of these flaked materials the grain is first submitted to a cleaning process, and is then broken up by machinery into small pieces, in which form it is known as grits. In the case of maize this is preceded by the removal of the germ, which contains the greater part of the oil, this being objectionable from the brewing point of view. The grits are then subjected to the action of steam whereby they are thoroughly softened, after which they are converted into flakes by being passed between hot rollers and finally dried. The main result of this steaming process is to break up the cell structures of the grain and to gelatinize the starch, and so render it amenable to the action of diastase at the comparatively low temperatures of the mash tun. Occasionally, however, grain which has not been subjected to this cooking process is employed, as for example maize grits, broken rice, oatmeal (in oatmeal stout), and rarely barley. In that case the starch is not in a condition to be acted on by diastase under the ordinary mashing conditions, and it becomes necessary to submit the raw grain in question to independent treatment in a separate vessel known as a converter. In this vessel the grain, mixed with a small proportion of pale or active malt, is slowly heated with water to about 180° Fahrenheit by means of steam, and is kept at that temperature for a little while, after which it is raised nearly to boiling. The object of mixing a small proportion of pale malt with the grain is in order that the liquefying diastase of the malt may convert the ordinary starch into the soluble form, and so prevent the grain mixture from becoming unduly viscous when cooled down to the temperature at which it has to be run into the mash tun. The starch is now in a condition to undergo saccharification by the malt diastase, and the thin gruel is consequently run into the mash tun with the malt grist and mashed in the ordinary manner. In this country the system of mashing known as the infusion system is almost universally adopted, but on the continent of Europe and in America a process of decoction is very largely employed. In the infusion system the ground malt, with other prepared grain, if such is used, is merely mixed with the requisite quantity of water at the most suitable temperature, and the action is allowed to proceed until conversion is complete and until wort of the required composition has been obtained, after which the wort is run off and the residual grains are sparged, the temperature rarely, if ever, rising above 165° Fahrenheit. In the decoction method the malt is usually mixed with the water at a lower temperature than is customary in infusion mashing, and the temperature of the mash is raised by successive stages nearly to boiling. In some cases this is done by transferring a portion of the mash to a copper and after heating it to boiling, returning it to the mash tun, whilst in others a proportion of the clear wort is run off so as to preserve a sufficient amount of active diastase, after which the contents of the mash tun are raised to a high temperature by means of steam, and when cooled sufficiently the active wort is run in and the mashing allowed to proceed. It will be seen that an important difference between these two systems lies in the fact that in the decoction method the mash is raised nearly to the boiling point of water, and so any imperfectly modified grain is gelatinized and rendered amenable to the saccharifying action of the diastase. It follows that with ordinary malts, which, no matter how carefully made, are apt to contain a little unmodified grain, the decoction system yields higher extracts, that is to say, gives a rather greater proportion of soluble matter than the infusion. It is, however, very generally held that decoction mashing is not so well suited to the production of English beers as the method ordinarily followed, and in this there is some truth. The mashing having been completed, the bright wort is run off from the insoluble portion of the grain into the copper where it is boiled with hops. As the strong wort runs off, hot water is sparged on the residual grains so as to extract as completely as possible the whole of the soluble matter, and this too runs into the copper. The brewer, knowing the proportions of extractive matters yielded by the malts and other materials he is using, is easily able to calculate the total quantity of water necessary to produce the required volume of wort at the requisite density. The density of the wort, as will be seen later, determines the strength of the beer to be brewed, and as taken in the fermentation tun prior to fermentation, constitutes what is known as the original gravity of the resulting beer. The sparging process, to which reference has been made, consists essentially in washing out of the grains the soluble matters which have been formed during mashing. Care has to be exercised not to employ water at too high a temperature, since small quantities of unconverted starch left in the grains would be gelatinized and brought into solution, and as the small amount of diastase remaining might easily be rendered inactive, such starch would pass into the wort and might cause some difficulty in connection with the brightness of the beer. As a rule sparging commences at a temperature of about 170° Fahrenheit, which is somewhat in excess of the average mash temperature required, since some heat will have been lost during the period of standing, and this has to be made up. At the end of sparging the temperature of the residual grains, or goods to use the term usually employed, will be about 160° Fahrenheit, and the density of the last runnings, if the operations have been properly conducted, will not exceed 1002° or 1003°. In the case of strong beers, however, when less sparging water has been used this final gravity may be somewhat exceeded. The spent grains left in the mash tun when sparging is finished contain a little starch, the amount depending on the thoroughness with which the malt has undergone modification during the malting process, and on the success with which the mashing operations have been carried out. They also contain the insoluble proteins of the malt, a little oil from the malt, and a good deal of digestible fiber. They have consequently a moderately high cattle feeding value, and are readily purchased for that purpose by farmers and others. Sometimes they are bought in their wet condition, with about 75% of water, but more often they are first dried, since in this condition they will keep good indefinitely, the wet grains rapidly becoming sour and unpleasant, particularly in the summer. The following may be taken as representing the average composition of dried spent grains as obtained in the ordinary infusion system of mashing. Starch, 4.15. Digestible fiber and gum, 36.0. Fat and oil, 6.5. Albuminoids, proteins, 18.4. Ash, 4.12. Moisture, 8.96. Crude fiber, 21.87. Total, 100%. Such a product has a combined feeding and manurial value represented by about 102 units. Compare say with 104 for an average sample of wheat. End of chapter 3. Of Brewing by A. Chaston Chapman. This LibriVox recording is in the public domain. Read by Marianne. Chapter 4. Boiling. The wort from the mash tun having been collected in the copper is ready to be submitted to the boiling process. Sometimes the wort passes through an intermediate vessel known as a receiver or underback, from which it either flows by gravity or is pumped into the copper. The use of such a vessel is determined very largely by the construction of the brewery and the relative positions of the mash tun and the copper. Technologically, the use of such a vessel has no special significance, and the only point of any importance is that the wort shall not be allowed to remain for any length of time in it at or below the temperature at which it leaves the mash tun, since the diastic action would, in that case, obviously be proceeding the whole of the time, and a larger proportion of fermentable carbohydrate matter would be produced than might be required. In order to avoid this it is customary, in cases where the wort does not flow directly into the copper, to provide the receiving vessel with a steam coil by which the wort can be immediately heated to a temperature at which the diastase becomes inactive. Thus the wort when it reaches the copper will have practically the same carbohydrate composition as when it left the mash tun. The copper may either be an open or a closed vessel capable of holding the whole or a part of the brewing. In the former case the whole of the wort is boiled in one operation, but in the latter 2 or even 3 boilings may be necessary, the stronger wort being boiled first and the weaker wort subsequently. The copper is boiled either by fire or by steam, and as a rule a boiling period of about 2 hours is adopted. The objects of the boiling process are the following: A. The sterilization of the wort. B. The arresting of the action of the diastase. C. The extraction of the flavoring and preservative constituents of the hops. D. The precipitation of undesirable protein matters, and E. The concentration of the wort to the requisite point. It will probably be conducive to clearness if the above 5 objects are dealt with separately, but before doing this it may be convenient to devote a little space to a description of the hop plant, or at least to that portion of it which is used by the brewer. The hop belongs to the Cannabaceae, but it possesses certain affinities with the stinging nettle, and is consequently occasionally classed with the Urticaceae. It is probable that hops were grown and used chiefly, perhaps, for medicinal purposes at a very early period. Occasional references to hops and hop gardens occur in documents of the 9th century, and it seems not improbable that even at that early period they were occasionally used for the bittering of beer. By the 13th century the area under cultivation had apparently increased very considerably, and in the 14th century there is plenty of evidence that hops were employed for the bittering of beer, at any rate in Germany and in Holland. It is generally supposed that hops were first introduced into England towards the close of the 15th century, but that they were not received with open arms is evidenced by the fact that both Henry VII and Henry VIII prohibited their use in beer. This ban appears to have remained in force until the reign of Edward VI, when the restrictions as to the employment of hops in brewing were removed and their cultivation was very considerably extended. The common hop is dioecious, that is to say, the male and female flowers are produced on separate plants. The female flower, which alone is used by the brewer, consists of a cup-shaped corolla with a round ovary containing one seed. A considerable number of these flowers grow together in the form of cones, which are technically known as strobiles. It is these strobiles which constitute the hop as used by the brewer and which contain the various constituents which are of so much importance. The following illustration, Fig. 2, represents the structure of one of these strobiles. Number 1 shows a full-grown strobile consisting of an axis or strig on which are arranged bracts of two different kinds. The one class of bracts, B, contains the fruit or seed of the hop, whilst the other, SB, is seedless. The hop axis or strig is shown in number 2, whilst number 3 and number 4 show the manner in which the bracts are attached to the strig. At the bases of the bracts will be found a yellowish powder known as lupulin, which, when examined microscopically, is found to consist of granules of regular shape and well-defined structure. This yellow powder, which is usually spoken of by the brewer as condition, is of the greatest importance since it contains the bulk of the constituents on which the brewing value of the hop chiefly depends. Other things being equal, therefore, the commercial value of a sample of hops is roughly proportional to the amount of lupulin which it contains. The percentage of lupulin in different hops is subject to very considerable variations. In old hops it may be as low as 2 or 3%, whilst in new and rich hops it may occur to the extent of 16% or more. It contains the essential oil, resins, wax, bitters, and a number of nitrogenous bodies, including one or perhaps more alkaloids. Of these constituents the essential oil, certain of the resins, and the bitter principles are of special importance, the essential oil and bitter substances being the chief flavoring constituents, whilst certain of the resins are markedly bactericidal and so confer on the hops their well-known preservative properties. The essential oil occurs to the extent of about 0.3 to 0.6 parts per 100 parts of the hops, or rather it should be said that this is the amount that can be obtained from the hops by distilling them with steam and recovering the oil from the aqueous distillate. The oil consists, as the author has shown, of two hydrocarbons, myrcene and humulene, inactive caryophyllene, and of several oxygenated substances, which are present in comparatively small proportions, but on which the odor of the oil is largely dependent. These oxygenated constituents vary somewhat in oils of different origin, and it is due to this variation that a sample of oil obtained from say Californian hops differs appreciably in odor from one prepared from Bavarian or Kent growths. The hydrocarbon myrcene is a very mobile liquid having a penetrating and not unpleasant odor, and undergoes conversion into a non-volatile, resinous substance on exposure to the air. As this change takes place with great readiness, and as the myrcene constitutes about 40 to 50% of the fresh oil, it will easily be understood that the yield of volatile oil from hops a few months old is very considerably less than from the same hops when freshly picked. The humulene is a representative of the class of substances known as sesquiterpenes, and when pure possess very little odor, nor does it undergo any appreciable change when exposed to the air. It is usually present in fresh oil to the extent of about 40%. The oil is almost insoluble in water, about 1 part in 20,000 parts, but it dissolves a little more readily in a weak alcoholic liquid such as beer. Slight, however, as its solubility is, it is yet ample for flavoring purposes, for, as with most essential oils, its odor and flavor are most apparent when it is in a highly diluted condition. I have pointed out that it is volatile with steam, and as might be supposed it is very largely lost when the hops are boiled with the wort, almost the whole passing away into the air with the escaping steam. The fragrant smell in the neighbourhood of a brewery when the wort is being boiled affords some evidence of this. To minimize the effect of this loss, most brewers are in the habit of adding a proportion of the best hops to the copper shortly before the conclusion of the boiling period. It appears very probable, however, that the flavour, other than bitter, communicated to the wort by the hops is due not so much to the volatile oil itself as to the solution of a small quantity of the resinous oxidation products of the oil, which are not volatile with steam, and which possess a smell and flavour very similar to those of the oil itself. In certain classes of beer it is customary to add a small quantity (1/4 pound or 1/2 pound) of hops to the beer in the cask, and in this case the oil will, of course, play a more important part, as some of it passes into solution and so communicates to the beer its characteristic flavour and aroma. It may be added that unlike many essential oils, the oil of hops does not possess any antiseptic properties. We now come to a brief consideration of those highly important constituents, the resins and bitter substances, which are not only flavouring agents, but which exercise the even more important function of preserving the beer from deteriorating effects of bacterial activity. The chemistry of these substances is lamentably incomplete, notwithstanding the large amount of work which has been devoted to their study. 3 distinct resins have been up to the present isolated, known respectively as the alpha, beta and gamma resins, the first 2 being possessed of antiseptic properties and the last being devoid of any such power. For technical purposes it is customary to distinguish merely between the so-called soft and hard resins, the former being soluble and the latter insoluble in light petroleum. It is to the soft resins that the preservative properties of the hop are ascribed. This division is not a very scientific one, for both classes of resin unquestionably consist of a number of substances about which little is known. It has nevertheless the advantage of being convenient, and does to some extent at least connote a difference which is of technological importance. The soft resin is an exceedingly unstable substance and tends to pass very readily into the hard. This change occurs in the hops during ordinary storage, and it is to this that the greatly reduced preservative value of old hops is due. It has been found that when hops, instead of being kept at ordinary atmospheric temperatures, are stored at temperatures between 30° Fahrenheit and 40° Fahrenheit, the activity of the various chemical changes which produce such marked deterioration is greatly reduced. The following table, due to Briand, shows for example the influence of temperature on the proportions of soft and hard resins in the same hops, when stored for the same time. Hops as put in bottle. Soft, 11.75. Hard, 3.16. Total, 14.91. A. Hops stored 7 months at 72 to 75° Fahrenheit. Soft, 8.82. Hard, 5.94. Total, 14.76. B. Hops stored 7 months at 55 to 65° Fahrenheit. Soft, 9.21. Hard, 5.15. Total, 14.36. C. Hops stored 7 months at 35 to 40° Fahrenheit. Soft, 10.67. Hard, 4.20. Total, 14.87. D. Hops stored 7 months at below 32° Fahrenheit. Soft, 11.10. Hard, 3.57. Total, 14.67. At the present time, very large quantities of hops are cold stored as soon as bought, and the brewer is then able to avail himself late in the season of a material possessing preservative powers but little inferior to those of the original hop. In close genetic relationship with these resins stand certain substances of acid character, several of which have been obtained in a crystalline condition. These are the so-called hop bitter acids. These substances, like the resins, are characterized by great instability, passing readily into resins, either on exposure to air or when boiled with water. One of these acids yields mainly valeric acid in oxidation, and it is to this that the cheesy odor of old hops is due. Since the preservative properties of hops do undoubtedly reside in the so-called soft resins, many attempts have been made to regard the percentage of these resins as the basis of a chemical evaluation of hops for brewing purposes. Speaking in general terms, it is unquestionably true that those hops, e.g., high-class Bavarian, Californian, etc., which contain the largest proportions of soft resin as determined by extraction with light petroleum, are those which practical experience has shown to have the strongest preservative properties in practice, and there can be no doubt that the method is, within certain limits, a very useful one. It cannot be denied, however, that it has its limitations, and much work will have to be done before the precise parts played by the various resins and bitter acids in the preservation of beer is fully understood. It has already been stated that the resins occur almost entirely in the lupulin, of which they constitute from 50% to 70% or more. Hops grown in different countries differ not only in the percentage of resin which they contain, but also in their aroma, which depends on the precise composition of the essential oil, a fact which often influences the brewer in selecting the blend of hops to be used. Hops, like very many other plants, contain tannin in amount varying from 3% to 5 or 6%. At one time considerable importance was attached to this constituent, since it was thought to be a potent factor in the coagulation and subsequent removal of undesirable protein matters from the wort. That it is operative to a small extent in this direction is true, but there is no ground for supposing that any definite connection exists between the richness in tannin of hops and their value to the brewer. In addition to the above constituents, hops contain gum-like bodies and a number of nitrogenous compounds, the precise significance of which in brewing technology is not yet completely understood. It had long been known that the addition of a small quantity of fresh hops to beer in cask was usually followed by an outburst of fermentation, a fact which did not receive an adequate explanation until Brown and Morris showed that like most plants they contain diastase, which, of course, converts some of the maltodextrin present into readily fermentable maltose. With this brief account of the more important constituents of the hop, it will now be possible to understand the general character of the changes occurring during the boiling process, and it will perhaps conduce to clearness if we consider seriatim the 5 objects given on page 45. The first, and not the least important, is the sterilization of the wort. It will be readily understood that the wort when it reaches the copper contains enormous numbers of living organisms of many kinds, chiefly bacteria, yeast, and molds, derived from the surface of the malt and other materials used in the mash tun, the mashing temperatures being as a rule too low to effect the destruction of vast numbers of such organisms. Although hopped wort does not constitute a very favorable medium for the development of many of these, and beer is still less favorable, yet those capable of developing would be sufficiently numerous to render the finished beer bad and undrinkable in a very short time. During the boiling period, however, these are all destroyed, and the wort when it leaves the copper is perfectly sterile, that is, it contains no living organism of any description. The second object of the boiling process is to arrest the action of the diastase. It has already been pointed out in the previous chapter that the character of the beer produced is very largely dependent on the nature of the carbohydrate constituents of the wort when it leaves the mash tun, and that this in turn is dependent upon the extent to which the diastase of the malt has been allowed to act upon the starch. This part of the process is capable of being closely controlled by the brewer, who is able to so adapt the conditions to the material to be used as to produce a wort having just the degree of fermentability required. Since the diastase is not destroyed at the temperatures of the mash tun, but retains much of its activity in the wort, it is clear that unless steps are taken to arrest this activity, the conversion process taking place during mashing would continue, with the result that unduly large proportions of maltose would be formed and the resulting product after fermentation would be merely an alcoholic liquid, with little or none of the reserve carbohydrate material needful for cask fermentation, and possessing none of the characters of beer. On boiling, however, this diastic activity is completely arrested, and so the composition of the wort is fixed. In regard to the third object mentioned on page 45, namely the extraction of the flavoring and preservative constituents of the hops, it will not be necessary to say very much, in view of the description of those constituents which has been given above. From what has been said it will have been gathered that the bittering and preservative constituents of the hop are not clearly distinguishable, but that both sets of properties are resident in the bitter acids and resins. Owing to their great instability, these substances are quickly decomposed in the copper, becoming largely converted into antiseptically inert substances, and consequently their subjection to a prolonged period of boiling is objectionable. On the other hand, the full bittering effect is not so easily obtained, and consequently the brewer is compelled to adopt a procedure which is in the nature of a compromise. That is to say, some of the hops are added at the commencement of boiling, the remainder, usually the best, being added shortly before the completion of the process. In this way it is probable that the best results are obtained from the hops, both in respect of preservation and flavoring. Reference has already been made to the advantage of this procedure in reducing to some extent the loss of essential oil. The quality of the hops and the proportions used will naturally depend upon the class of beer to be brewed. Thus, in the brewing of stock pale ales and bitter beers, larger quantities of hops, and those of superior kinds, will have to be used, than in the case of mild beers. The reasons for this are twofold. In the first place, the former beers must have more hop flavour than the latter, and in the second, they are usually expected to remain sound for a much longer period, and consequently need more of the preservative constituents. In beers brewed for export, this is particularly the case, since such beers are often exposed to a very great strain, as for example in tropical countries, and in their production large proportions of the best and strongest hops are invariably employed. It may not be out of place to refer here to an important difference between the great bulk of the beer brewed in this country and the lager beer of the continent and America. The latter beer, when brewed, is kept for a considerable time, often some months, in casks stored in cellars kept nearly at the freezing point. When this lagering process is complete the beer is transferred to the trade casks, and it must be quickly consumed, if it is to be drunk at its best. In the brewing of these beers the continental or American brewer uses a much smaller proportion of hops than is usual in this country for stock beers. The reason being that whilst the English brewer has to rely almost entirely on the hops for the keeping of his beer, the lager beer is preserved by being kept at very low temperatures. We may now consider the fourth object of boiling, that is, the precipitation of undesirable protein matters. The mash tun wort contains nitrogenous substances of many kinds. Together with such comparatively simple substances as amino acids and amides, it contains soluble and non-coagulable products of protein hydrolysis, such as proteoses and peptones, and finally more complicated proteins which though soluble in the wort at the temperature at which it leaves the mash tun are converted into insoluble substances, coagulated, on boiling. It has already been pointed out that during the malting germination process the proteins of barley undergo considerable change, being converted by the proteolytic enzymes of the grain into simpler and more soluble products. The resulting malt, therefore, contains a much larger proportion of its nitrogen in the form of soluble and non-coagulable products than is the case with the barley from which it has been made, and this process of enzymic hydrolysis and simplification proceeds during the mashing process. Many of these simpler nitrogenous substances are necessary for the nutrition of the yeast during the subsequent process of fermentation, and their presence in the wort in sufficient quantity is therefore of the highest importance. The more complex proteins, however, are so far as is known useless for the purpose, and as their presence in the finished beer could only have the effect of seriously diminishing its keeping properties, to say nothing of its brilliancy, their removal is in the highest degree desirable. Fortunately these proteins are rendered insoluble on boiling and can, therefore, be readily removed when the boiled wort is subsequently filtered in the hop back. The last object of the boiling process is to effect the requisite concentration of the wort. In order to wash out of the grains in the mash tun the whole of the soluble saccharine matters, it is necessary